Hi there, this is a video for my grade 12 pre-calculus students, and this is our introduction to chapter 7 and 8. And yeah, we're getting to the point in the course where we're down to our last 7 weeks of classes, and we're not going at the same pace we'd be going if we were having regular classes. So I'm going to trim a little bit of the fat off this course. Namely, I think we're going to kind of skip a lot of the graphing that's left in the course. We did a whole lot of graphing at the beginning of the course and transforming functions. I think from here on out, those of you going on to first year university math are going to be better served if we really focus on the algebra and the number skills that you're going to need to be successful in your first year courses. So with that in mind, I've kind of squished together chapter 7 and 8. And we're going to call it exponential and logarithmic functions. And we're going to start fairly easy. So those of you still getting over the test that you wrote are going to find this a fairly quick and hopefully fairly painless introduction. In fact, why don't we start by having you see if you can fill in these 8 blanks. Maybe pause the video and get your answers to them. How'd you do? So let's see. Remember that when you multiply together two powers, you add their exponents. Oops. And power of a power means you multiply your exponents. This is the quotient rule, which means that you subtract those exponents. A lot of people fall for this, and anybody put x to the 5. Does everybody get why this isn't x to the 5? Think about it. This is x times x times x times x 15 times, and this is x times x times x. 3 of these x's cancel 3 of the x's on top. It doesn't leave 5 x's, it leaves 12 of them. And remember, as long as all of the following examples have an x and y that isn't 0, any number in the universe that isn't 0 to the power of 0 is 1. Now, what can I do with this thing? Well, remember, I can distribute that squared, and I can distribute this cubed. And you know what, just for fun, I almost put this on in your notes. I almost added another line here where I would have asked you to do this and see if anybody fell for it and erroneously wrote down after doing those two, see if you just sort of kept on trucking and did this. If you honestly think that this equals this, I don't know how you got this far into grade 12 math, because that is a mistake that is beneath you. Right? You can distribute a power through a product, you can distribute a power through a quotient, but you cannot distribute a power through a sum or a difference. Those are not equal. All you have to do is pick two numbers. How about 3 and 4? If x was 3 and y was 4, 3 plus 4 is 7, and 7 squared is 49. Is 9 plus 16 equal to 49? No, it is not equal. Try any other two numbers you want and just subtract, and you'll see it's not equal either. Everybody should know that if you are going to square a binomial, you actually have to expand it and multiply it out. So make sure you remember that there is such a thing as a power of a product rule, a power of a quotient rule. There is no such thing as a power of a sum or a difference. So with that in mind, did you remember what to do with this thing? This is, of course, a radical. This is either the cube root of x squared, or, if you like, you could write it as x squared, or let me rewrite that better. That's exactly what I wrote the first time. I could call it the cube root of x, and then square that. It doesn't matter what order I do those two things in. Just remember that the power of 1/3 is a cube root, the power of 1/2 is a square root, the power of 1/4 would be a 4th root. Another way you could think of this is you could think of it as x squared to the power of 1/3, because 2 times a third is 2/3. In other words, I'm just sort of using that rule right there. And then finally, lastly, do you remember what a negative exponent does to a base? Yep, makes it a reciprocal. So those are your crazy 8, your 8 rules for exponents and exponentiation. So hopefully you have a pretty good handle on that. The other thing that I would hope you have a pretty good handle on, because we won't be letting you use a calculator for all of this unit. In fact, most of it will be calculator free. And those of you moving on to first year math courses, again, they'll expect you to be able to do these kinds of manipulations without the aid of a calculator. So they'll expect you know some common numbers. So I won't bother filling this in for you because you can always check your answers with a calculator. But see how many of these you can do without touching your calculator. Hopefully powers of 2 should be pretty easy. But how are you with powers of 3, 4, 5, and 6? Notice we don't expect you to know as many powers of 3 or as many powers of 4. And of course, if you've forgotten how to do something like, for example, 2 to the power of 5 on your calculator, remember that you should have, on every scientific calculator, something like this button here, a power button. So 2 to the power of 5 is going to look like that. Remember that it's not 10, because it's not 2 plus 2 plus 2 plus 2 plus 2. It's 2 times 2 times 2 times 2 times 2. Remember that an exponent, at the end of the day, is a repeated multiply. Cool. So that first page you can kind of just deal with on your own from there. Let's get into something a little more interesting. If I have a base to an exponent and then the same base to a different exponent and I'm told that they're equal, then x must be equal to y. So if I have an equation along the lines of 3 to the power of x plus 2 equals 3 to the 7, because that's the same base, so 3 times a number this many times is equal to 3 times a number that many times. Well, if they're equal, these two amounts must equal each other, so I can turn them into their own equation. So how do I do that for, oh, I've frozen. No, there we go, I'm back. How do I do that for this guy? Well, notice that right now this and this aren't the same base, but again, I should recognize 32. Remember, I just punched it in the calculator. It is 2 to the 5. So once I have made that happen, I can just say that x plus 1 equals 5. Now I'm going to, again, break off into scrap paper, and if I was marking your work and you were doing this question and you did this, do you know what I would do? I would take off half a mark. Why? Because I'm a meanie. No, because you've actually said something mathematically wrong. What does it mean to cancel things in math? I almost wish we didn't use the word cancel. Cancel is a shortcut for two things that we do in math. If we have a situation algebraically where we add something to itself, or we subtract something from itself, we add opposites, we say that those numbers cancel. In other words, they add or subtract to 0. We also use the word cancel when we are multiplying. We say that those 3's cancel. Actually, we could even say it's a divide. This cancels because 3 divided by 3 is 1. So you either have the identity that two things divide and make 1, or two things add and make 0. Neither of those two things happened there. I did not make those 2's disappear by adding them to make 0 or dividing them to make 1. Those 2's didn't disappear. I just picked up these two parts and made a new equation. So keep that in mind. Please don't put a cancel sign through those. Somewhere down the line, if somebody sees you do that, they'll say, oh my God, who taught you grade 12 math? And then it'll really reflect badly on me. So for my reputation as a teacher, please don't cancel those 2's. Understand that you are just making a new equation out of this and this. And of course, it's a pretty easy equation. I just minus 1 from both sides. And then x is equal to 4. And let's just plug that in. Is that true? Like, we can always do a check on that, right? We can do a verify. Put the 4 in where the x is. And 2 to the 4 plus 1 equals 32. And 2 to the 5 is equal to 32. And yeah, I already punched that. I know it's true. Cool, huh? All right, let's do one that's a little more complicated, a little tougher. It's got an extra step in it. 3 to this power is equal to 27 to that power. Any ideas? I heard somebody say it. 27 is also 3 to the power of 3, right? 3 times 3 is 9. 9 times 3 is 27. So does everybody get what I did here? I replaced 27 with 3 cubed, and since this 27 is being taken to the power of 2x, this 3 cubed is being taken to the power of 2x, so that's my power of a power rule. So this is 3 to the 4x minus 1 equals 3 to the 3 times 2x, which is 6x. And once again, now that the bases are the same, and that's key, I can't stress that enough. I can only do this next step because the bases are the same and there's nothing else in the equation to change the equality of the situation. 3 times itself this many times is equal to 3 times itself that many times. So I can make an equation where this equals that. And then I'm going to minus 6x from both sides, add 1 to both sides, and divide both sides by negative 2. And hey, that's a negative fraction for an exponent. Well, it wouldn't be a negative fraction once I punched it in. Again, if I wanted to do a check, and I do, I'm going to say 3 to the power of 4 times negative a half, and 4 times negative a half is negative 2, and 27 times to the power of 2 times negative 1/2, so that's 3 to the negative 3 equals 27 to the negative 1. And remember what exponents that are negative do? They make reciprocals. And that would be 1 over 3 cubed. And yes, those two things are the same because 3 cubed is 27. So yep, that's my answer. Cool, huh? All right, let's look at example 3. 3 to the power of x times 27 equals 81 to the power of 2x minus 1. I'm going to do all kinds of fun things to this one. I'm already thinking 3's. Why am I thinking 3's? Because that's 3 cubed, and that's 3 to the power of 4. So this is 3 to the power of x times 3 to the power of 3 equals 3 to the power of 4 to the power of 2x minus 1. Isn't that cool? What can I do with these guys? Oh yeah, when you multiply two things that have the same base, you add their exponents. And what do I do with these guys? Oh yeah, when you take the power of a power, you multiply their exponents. And think about what I just did. I just did 4 times 2x minus 1 and distributed it like that. That's going to clutter up my work. I want to save that space for when I do my check. There. So now I can say that because the bases are the same, I can just make a new equation. And then I'm going to minus 8x from both sides. I'll finish it down here. And then I'll minus 3 from both sides. Divide both sides by negative 7. And x is equal to 1. Let's do a check. See if that's true. And then let's misspell the word check. Yeesh, sorry. So 3 to the power of 1 times 27 equals 81 to the power of 2 times 1 minus 1. So that's 3 to the 1 times 27. 3 27s is 81. And 81 to the power of 1 is 81. You betcha. That is correct. Okay. More fun. Let's get some radicals involved. All right, what do we do with that? Well, I'm seeing 2's. That is 2 squared. And this guy is 2 to the x times 2 to the 1/2. So 2 times x plus 1 is 2x plus 2. And x plus a half looks like that. So I can now say that 2x plus 2 is equal to x plus a half. I minus x from both sides. I'm just going to work over here. I'm going to minus x from both sides, leaving me x. I'm going to add negative 2 or minus 2 from both sides. A half minus 2 is negative 3 halves. Now, I'm getting to the point where I don't know that I'm going to be able to do these checks much longer. The checks are going to start to get to the point where they are far more complicated than the algebra I'm doing. But I'm game to give it one more go here. Let's see. That's 4 to the negative 3 halves plus 1 is equal to 2 to the negative 3 halves root 2. Well, isn't that special? That's negative 3 halves plus, remember 1 is 2 halves, so that's 4 to the negative 1/2, which is 1 over the square root of 4, which is 1/2. Can I turn, I shouldn't put equals on that side, that's bad form. Can I turn this side into a half? Maybe. Well, let's see. This is root 2, that's this root 2 here, over, I'm going to take that and make it the square root of 2 cubed. I'm onto something here. What's going to happen then is I'm going to look at the top of this and say that that's root 2, and down here, I'm just going to expand that. That's root 2 cubed, which is root 2 times root 2 times root 2. Those two cancel. That's in a proper use of cancel. And root 2 times itself is 2. So, yep, that is the right answer. I think you can kind of see now what I meant when I said that eventually we'll get to the point where trying to do a verify is probably uglier than actually solving the question. So, I will probably start to just rely on my skills and maybe not so much with the checks. But keep in mind, if you're good with arithmetic and you're good with your power laws, the checks should work. All right, what am I going to do with this guy? Well, I'm seeing 3's, right? Because 81 is 3 to the 4. And I can rewrite this as 3 to the negative x minus 1. And be careful, notice that I actually put that x minus 1 in a bracket, because I'm going to have to sort of distribute that and come out to that. And now I can turn that into the equation negative x plus 1 equals 4. So negative x is equal to 3. So x is equal to negative 3. And like I said, I'm not going to bother checking that. I can actually kind of see that it's going to work. Okay, finally this guy. Isn't that fun? What am I going to do with that? Well, I'm seeing 2's. How about you? Do you see 2's there? 8 is 2 to the power of 3. Now, let's be careful with this negative here. I'm going to just kind of peel off onto some scrap paper and just remind you of one other thing that maybe I should have stuck in the power rules, but it's not really a power rule so much as it's a coefficient rule. Do you remember way back in grade 9, your grade 9 teacher tried to teach you the difference between these two things? Do you remember what the difference between them is? There might be people going, but they're the same thing. No, they're not. This is saying, on this side, that I have the negative of 2 times 2. Remember, BEDMAS would say that an exponent counts before a negative, before a subtract? If you like, think of it as 0 minus 2 squared. That's definitely negative 4. Here, the negative is part of the base. This is negative 2 times negative 2, and a negative times a negative is a positive. These two things don't say the same thing. That's an important thing to understand when I start looking at this guy. Does this negative get affected by this power? No, it doesn't. So this is the negative of 2 cubed to the 5/3. Make sure you don't shove that negative into this bracket when you do a question like this, okay? Because in this case, it wasn't part of the base. Over here, that's 2 times 2 squared to the power of x over 2. Okay. Remember how you do power of a power? You multiply those exponents. So 3 times 5/3, those 3's actually, you could say, cancel. So that's going to be 2 to the 5 with a negative out front is equal to, and you know, at this point, I should recognize that, Houston, I've got a problem. Anybody see the problem yet? All right, I'll keep going. I'll divide those 2's, because, you know, I'm multiplying 2 by x over 2, which is going to be 2 times 2 to the x. So now I have negative 2 to the 5 equals 2 to the power of 1 plus x. So I'll just write that as x plus 1. Anybody see the problem yet? Why no solution? What's going on? Why can't I solve this thing? Well, think about it. This is not quite the same as that. I know what you're saying, hey, you just told me a minute ago that this negative wasn't part of the base, right? And it's not. So this base is the same as this base. But look at it from a bigger perspective. As an equation, I have a negative equals a positive. The only way this has any solution is if I can come up with some sort of x, some sort of exponent that 2 times itself that many times will be a negative. Because this side is negative 32. How many 2's do you times together to get negative 32? Well, I'll tell you what, you could multiply 2 all you want. You can't multiply positives and get a negative. No solution. 2 to the x plus 1 cannot equal negative 32. Haha, that one was trying to fool us. Now, up to here, we're basically still dealing with, we're dealing with some fairly fancy algebra here, but everything's based on the power laws that we learned in grades 9 and 10. We have not yet solved or learned how to solve equations where I have exponents that have variables in them and the bases are not the same number. That's coming up later on in this chapter. So that takes us to the end of 7.3. You can try the 7.3 questions in the first page of your new exercise book. Thanks for watching, everybody. Have a good day.